There's still no sound. Oh, no, there's sound. Hi. Hi, everyone. So good to see so many people. That's absolutely amazing. It's great to be back at TechTown. It's quite a few years since last time I was here. And to come back and see all these beautiful people, that's just amazing. So my name is Dyre Bjerknes, and I'm going to give this talk, which is called Swarmfare, when the shit hits 1,000 fans. So let's just dive straight into that a little bit. So as you perhaps know, we have in Norway something called the Norwegian Defence Research Establishment, sometimes referred to as FFI or Forsvarets Forskningsinstitutt. And once per year, FFI publishes an article about the defense analysis of Norway. What do they believe is going to be the future? What is important for the Norwegian defense? And this year's report came out in February, and it's a really interesting read. So let's just take a look at some of the headlines in that report. Because if you read that text in its totally, you will see that submarines are mentioned 5 times in that text. And that makes sense. We are buying new submarines at the moment. Some of you here are maybe even working on that project together with the ThyssenKrupp. So that's an important thing for the Norwegian defense. If you read further, we will find that the Arctic areas in Norway are mentioned 15 times in that report. And that also makes sense because the Arctic is super important for Norwegian strategy and so on. What I find fascinating as someone who is working with swarm robotics and so on is that swarms are mentioned 18 times in that report. So swarms, swarm robotics, swarm intelligence is super important for what's happening in the Norwegian defense right now. And this is, of course, also partly due to what happens in Ukraine at the moment. We can every day read articles where hundreds or maybe even thousands of drones come coordinated from Russia over into attacking Ukraine. So how do we coordinate these swarms and how do we defend ourselves against them? And what are these swarms in the first place? So that's what I'm going to try to expose in this little talk. And I don't have that much material, so we're probably quite good on time. So if there are questions while I'm talking, or if there are things that you think are unclear, just feel free to reach a hand in the air, and we can make this into a kind of huge colloquium, kind of discussion, academic style group. That's going to be great fun. Okay, yeah, you are laughing. You're not used to this. Okay, so this presentation has in main 2 parts. I'm going to spend a lot of time talking about biology because a lot of the stuff that happens in swarm robotics and swarm intelligence have deep roots in biology. So we're going to look far into the past and see where are these swarms coming from. And then we're going to, at some point, we're going to pivot that into how can we actually use these lessons from biology to build genuine swarming systems for defense today. So that is the kind of 2 main parts. And then I will probably lose track sometimes and diverge into all possible different directions. So just be patient with me. I think we're going to have a good time. So let's go a little bit backwards in time. It's always nice to have some kind of historical anchoring in what we are doing. So this is basically a little schematic of the, we have to go back to the very beginning. This is the solar system. You know, the sun switches on around 5 billion years ago, and then Earth and Moon, and then there's stuff happening. And of course, now we are somewhere over here. And the question is, on this timeline, at some point collaboration arises. At some point evolution discovers that cooperation is a really, really useful mechanism for survival. And let me ask you, so when do you think that happened in history? Where on this timeline do you believe that, cooperation and swarming happened for the first time? Anyone who dare raise their hand? Yeah? Between 1 and 2. Yeah, so around here somewhere. Yeah, that's such a good guess that I'm gonna say that is pretty much correct. That is where it happened, because it turns out that at that time they were bacteria, and you may not know that bacteria are exceptionally social beings. They communicate, they collaborate, they cooperate to do whatever they do. And they have a mechanism that they call quorum sensing. And quorum sensing is basically that bacteria, when they are, for instance, you eat something that you really shouldn't have eaten, it gets into your body, and you have a little pathogen, a little disease in your body. And this little bacteria, when they are alone, they release a little chemical into the body. This is called an autoinducer, and this is reduced into your body. It's completely harmless. So your kind of self-protecting immune system doesn't react to it, so it just kind of passes by. But the bacteria uses this to signal to each other to know the relative number. So as they are living inside your body and they are splitting into 2, and now they are 4, and now they are 8, and they are growing and growing and growing, and constantly they are communicating with this autoinducer that your body doesn't detect. And at some point, there are so many of these bacteria that this autoinducer is just everywhere. And the bacteria then know that, oh shit, there's a lot of us. We are really many now. So when it reaches a certain threshold, within very short time, matter of minutes, all of the bacteria changes behavior at the same time. Very quickly. And trust me, no guys, you are gonna get sick. So one of the diseases that spreads this way is cholera. So you know that you eat the stuff, they are in your body, they grow and grow, then they signal when they reach the threshold, and then you get a really bad belly and you have to find a toilet really quick. And of course, this is the way these bacteria spread themselves, because you have a really liquid stool, it all flushes out, and then spreads and contaminates, and then maybe someone else get that contaminated water, and the cycle starts again. So this is a really old mechanism where this collective individuals uses as a way to collaborate and to spread themselves. So the mechanism of collaborations is really old. That is kind of the upshot of that little story. Of course, this doesn't happen only in bacteria. It happens on all kind of levels in creatures. So on the left here, we see a school of fish, thousands of fish swarming together, which clearly has some adaptation or adaptive benefits of collaborating like this. And here is from locusts that are grasshoppers that creates disastrous things in certain parts of the country. And the locusts are interesting because they have two phases in their life. One phase is when they live in their solitary phase, when they are alone and so on, and then they are just spreading around and populating as usual. But at some point when their density gets to a certain level, there's actually a new pathway being triggered in their genetics, and they grow wings and they change their body, and they get into what they call the gregarious phase, where they really start to repopulate at an immense velocity. And the biggest swarms that has been recorded of these kind of locusts are up to 8 billion individuals in a single swarm. And of course, this is disastrous for farmers and so on, because they just consume everything and they eat, tremendous amounts of food in their environment. I'm going to talk a bit one more biological example because it's my absolute favorite. And this is this little creature called Dictyostelium discoideum. I really need some credit for doing a 9-syllable Latin word without looking at the slides. I think I learned very quickly that I can't start a slide with it or start to talk with this because I'm too nervous and I can't spell it out, but no, it's all good. Anyway, so Dictyostelium discoideum, or Dicty, as we like to call it among friends, is a creature that are a amoeba. It's a single-cell individual. And they live as individuals, they eat, they split in two, just like single-cell animals are doing. But what's interesting about Dicty is that it has this insane life cycle. So they start up as individuals, we can see them up as feeding amoebas, then they are individual creatures. But when they have eaten all the food in the environment, something weird happens. Then they release what is called a CAMP, or a chemical attractor. They release this into the environment, and they use this attractor to coordinate their behavior. So they climb or they crawl together into huge lumps of this. So here's a microscope image from just a petri dish where they grow these things, and they aggregate into these things, and then eventually they form a slug. They become a tiny little slug that can crawl around. And what is really crazy about Dicty is that as individual amoebas, they are just stupid amoebas. But when they are in the slug phase, this little thing has rudimentary vision. So it will actually crawl towards a light source. And they discovered this by chance because there was a guy who was doing research on these amoebas. And there was another guy in the same lab, and he was doing research into fireflies. And they would discover that when they form a little slug, and they will always crawl towards the fireflies, and nobody could understand really what was going on. But what happens is that Dicty actually discovers or develops a rudimentary vision within hours of aggregating together. Anyway, so they migrate around a little bit. They will find a spot that they, for some reason, find suitable. And then they create this fruiting body formation. A part of the slug will attach itself with this kind of back end to the ground. And then they all crawl up into this little top, is what we saw on these images on the previous slide, where we have these little stalks, and they all climb up there, and they dry out. And at some point, that little thing bursts open, and it spreads with the wind, because now there are tiny little spores that are dry. So in a way, the Dicty uses collaboration and to a certain extent self-sacrifice to propagate themselves over distances that they impossibly could cover as individual creatures. So this collaboration, this self-sacrifice, and this life cycle is actually what helps them propagate into a larger area. I think that's kind of cool. So let's see, here it is, little Dicty out to, I know what they're doing. Having fun, probably. So what my point here is that collaboration as a mechanism for survival is absolutely ubiquitous in nature. It's everywhere on all possible levels, from bacteria all the way up to, even primates. And many years ago, when I did my research and my PhD on swarm robotics, I was very fascinated by Dicty. I was curious, can we use they as an inspiration to see if we can recreate these phenomena in robotics? So I started to set up experiments where I would say, can I actually do something like this? So we have a group of small robots. They are in some kind of arena, which is a 3 by 3 meter. We have a bunch of robots down here in the corner somewhere, and they're all confused. And then I want them to stay together as a coherent group, and I want them to traverse this entire arena towards a light source which is placed in the opposite corner of the area. But at the same time, they are really sensory constrained. So the robots have like a single sensor, which is binary and unreliable, telling the robots, am I being illuminated or am I in the shadow? Do I have any kind of information that I can go on? And they do not know the strength of the light, and they do not know the direction towards the light source. So they are exceptionally constrained in their knowledge. And the question is then, are we able to find a small set of algorithm behavioral rules for these individual robots such that they are able to stay together and move towards the light source? So that's what we try to do, and we use this little robot here, which is called an EPUC. They are made by EPFL in Switzerland. They're like 7 centimeters in diameters. They have some sensors and a couple of differential drive motors. They can go forward, backwards, and turn on the spot. And then the idea is that, we put a bunch of these together, then we put a light source somewhere over here, and then we try to program them in a way such that they collectively go towards the light source. And it looks, let's see if we can find the video. Here we are. And it looks something like this. So here is the light source. It's the black box on the right side. And then it's just a wooden frame, and they are driving around. This is sped up a little bit. It's a time lapse that takes a picture, 3 pictures per second or something like that. And they have been given a set of rules that makes them actually collectively go towards that light source. Even none of them have the faintest clue where the light source is. So this is sometimes what we call for an emergent property. The property arises from the interaction among the robots. And if you take the C code for the behavior of each robot, there is no mention of going towards a light source. There's no mention of position. There's no mention of anything. That is global. There's only how the robot should interact with each other given certain conditions. And then completely reliable, they go towards the light source. One of the things that we did with this was that we then started to use a radio link into the robots, and we started to destroy individual robots in the swarm to see how robust this swarm would be against fault tolerance or faults in the individual robots. If I take 10 of these robots and each one of them I make the sensor a little bit reliable, will they still be able to complete their overall goal and their task of going towards the light? And this thing is, for some type of errors, they are extremely robust. For other types of errors, the swarm broke down very, very quickly, especially partially failed. God, I'm talking fast, am I not? This is because I'm having fun. So let me ask you a question, maybe because we have the time. I think that we shall do a little exercise together. I think you should go together 2 and 2, 3 and 3, 4 and 4. And are you able to come up with a set of very simple behavior rules of how do these robots need to behave to be able to collectively go towards the light source? So is the question clear?
What's the sensor information again?
The sensor information, there's a binary sensor that tells if the robots are being shown light upon or whether it's not being shown light upon. And that sensor is kind of binary, single bit, no direction, no strength, no nothing.
What do you know about the other robots? Do you know distance between the robots?
Yeah, we can assume that. Yeah. So I think that, take 3 minutes, talk among yourself, and we'll recommence. Okay. All right, all right, all right. This is. Am I able to get your attention again? Ever so slowly, let's try to gather. Okay, I love to hear the energy in the room, and that is great. Oh, finally, there's quiet. Okay, yeah, you still want to solve the problem. Yeah, that's the enthusiasm. Okay, let these guys finish arguing. Now you're done? Okay, thank you, great. So anyone who want to volunteer of different methods to solve this, I know that there's someone back there who have solved it, but I will let someone else talk first. Anyone? Come on, don't be shy. We are friends here. Yeah.
Well, my thought was that they, if it's lit, they would try to get away from the cloud. While if it's not lit, it tries to go towards the crowd.
Towards the crowd. Okay, so for those who didn't hear it, he suggests that those who are on the kind of the leading edge of the group, they are illuminated because they're not casting any shadow. So they will tend to be a little bit shy compared to the other robots. And those who are in the darknet, they will be opposite of shy. They will try to gather together in a lump, and this dynamic will ever so slowly drift them in the right direction. Is that, did I understand that correctly? Yeah. And do you want to propose your suggestion? Was that quite similar?
It was quite similar.
Okay. Okay, and the lady behind you, I'm sorry.
So we were thinking that whenever the leading one, when the light hits them, they will start moving, and since they need a distance between each other, then the rest will see that the distance is increasing, and will try to move. And if they move in the opposite direction, they will detect that it's still increasing, which forces them to turn another direction until they find a direction that gets them
closer to the leading ones. Okay, so these are very similar suggestions, and they are very, very close to reality. It's exactly what we did, that the ones who are illuminated are generally have a larger avoid radius and kind of tend to pull away from the other robots. And those who are not illuminated will tend to try to stick together and therefore tags along on the one who pulls away. And the statistical pattern over time is that collectively they drift towards the light source, even though as individuals they have no clue where it is. So great, well done, thank you. And of course she knew. She's my former student, so it's so happy to see former students in the room. So it's good to see you here. Always great to meet students. So what we talked about so far in this talk are robots or entities that are relatively reactive. So these robots that we saw, they don't make a plan, they don't communicate, they don't negotiate, they don't do anything. They just look at their sensor, react kind of spontaneously or reactive to that without making a plan. And sometimes, sometimes the term that we use here is, instead of talking about robots or animals or bacteria, we just use the generic term an agent. So what we are, a different way of talking about swarm robotic systems is to talk about multi-agent system. That's a different term for the same thing. So what I'm going to do now a little bit, because we're kind of done with the kind of the reactive robotics inspired from biology kind of thing, I'm going to talk a little bit about strategic robots that can take part in different forms of strategic interaction. So what is a strategic interaction? There's this beautiful discipline called economic game theory, and game theory tried to model these kind of multi-agent systems. So one advanced mechanism for collaboration are auctions. And I don't know if you know this, but there are lots of different ways to do an auction. You're probably familiar with what is called an English auction, where you start on some price and then it's open so everybody hears the bids and you increase the value and then you get it. But there's decreasing auctions, there are sealed auctions where you don't know the bids of the others and so on. So these auction mechanisms, is the thing is that, you know, people have worked on this and we have been able, the collective, have been able to create mathematical models for auctions. We can actually model them in software and we can predict their outcome based on certain knowledge about the beliefs of the individual agents. So auction mechanisms are super central in analysis of multi-agent systems. So there was a beautiful research done a couple of years ago at the University of Oslo and the Norwegian Defense Research establishment, which was about task allocation. So in this case, we have a bunch of robots. They are driving around in some sort of environment and they find tasks to do. That can be cleaning something or destroying something or whatever. But sometimes when they find a task, it turns out they cannot solve the task by themselves because the task is too big or too heavy or too complicated, whatever. So then these robots need help from other robots. And the question is, how do we delegate that tasks among the robots in the most efficient way possible? And you could imagine that we have a case, something like this. This is from some music festival somewhere in Norway or maybe in Denmark, maybe it's Roskilde, I'm not quite sure. But when the festival is over, sometimes it looks like this because nobody cares about picking up the cheap shit, so they just leave it. And then someone else has to do the job. And you could imagine robots coming here and just cleaning up everything. But some of these tents are going to be too big for a single robot, so then it will have to flag and say, hi, I need help to get this tent packed down and thrown away, right? So what the researchers at University of Oslo did, it was a master's thesis by Mathias Mino Stensrud. Some of you may know him. He's been working in Kongsberg a few summers, I think, on summer jobs. What he tried then to do is to say, can we use auction as a mechanism to divide this task ideally among robots? So what happens is that this robot drives around, it finds a task too big for itself, and then what it does is that says, I'm in this location, who can help me? And it auctions the job away. And then the other robots can then bid onto that job. And what they are bidding is the time it will take them to get there and do the job. And then basically those who happen to bid the lowest time wins the auction and gets recruited to do the job. And of course, this happens then completely decentralized and self-organized, because the traditional way that engineers would solve this problem, and no offense, is that, you know, you would set up a control server and then all the robots would report in their problems that needed to be done, and then there will be some huge complex algorithm crushing all the possible positions and trying to calculate the optimal solution in a kind of brute force straightforward way. And of course that's fine if there's 10 or 20 robots, but if there's 1,000 it's going to be computationally complex. Anyway, but this case, you know, when the robots do it themselves, there is no central point. Everything is just done in a self-organized manner. And what Matthias found when he did this research is that when you do it in the self-organized way, you are getting maybe to the 95% of the performance of having central control. But it's exceptionally robust because you have removed the common mode failure point. If you take away the server, everything collapses. But when it's self-organized, you don't have that. So it becomes a much more robust system. There's a seat here if you want to sit up in the front. Oh, you're the photographer. Okay, I'm sorry. Okay, great. So this is, I think, a very good way where auctions is a mechanism for collaborations that's being used to self-organize works among autonomous agents. And just to kind of point forwards just a little bit, this is something which is also starting to happen in the battlefield. Because, you know, we send drones out, we want to destroy as many Russian tanks or fuel transports as possible, and sometimes a single striking drone doesn't have the firepower to actually destroy it, but it can create an auction and say, I see a high value target in this position, let's collaborate, and you auction that target away, and then other robots come in and they, you know, fix and finish that problem. So this is obviously something which is being thought about very carefully in military circles to apply these things straight onto the battlefield in a real conflict. So that's why these kind of things are important, right? Social choice theory and voting systems. This is also another way for robots, if they have different sensors, maybe they perceive the scene differently, and then they can use voting and this kind of social mechanism as a way to come into a coherent image and coherent understanding of the battlefield or the scene. So this is something being looked into a lot. Yeah, we made mathematical models for all different kind of voting system, you know, majority voting, sequential voting, all these different processes that industry could do this. And there's a course at university also that teaches this material, and I've been the external examiner on that course since it started in 2016. And one year we had a young woman coming in for her spoken exam, and you have a bowl and she draws the topic for her exam, and she draws, voting. And she's like, oh, I love voting, that's great. And it turned out that she found voting and this stuff so interesting that she convinced her family that they should do voting experiments for what to eat for Sunday roast every Sunday for many, many weeks in a row. And the family was clearly academically inclined, so they said, okay, let's do this. And then she would take all the mathematical models and she would deliberately manipulate the election for food every single week just to see what she could have for dinner. And she did not this because she wanted to make sure that she got the food she liked, but she did it to make absolutely sure that her younger brother would never get his favorite food. Yeah, so it's a very funny story. And I used to tell this story this way. And it turned out that maybe I'm exaggerating because I gave this talk a few weeks ago and she turned out to be in the audience. And she came up to me afterwards. I think you talked about me, but this is just, you're exaggerating way too much. So anyway, here we are. Micro and macro paradoxes. This is super fascinating. What happens all the time when we work in the field of multi-agent systems and micro and macro relationship. So of course, when you look into swarms at the micro level, we look at the individual behavior, the individual rules they follow. And when we look at the macro level, we look at the collective force of these kind of things. And constantly we see all over again and again and again that there arises paradoxes where you look at things from one point of view and you have one belief about reality. And then you change to the macroscopic perspective, it seems to be directly violating the underlying pieces that puts this all together. And there's a very famous example of this called Simpson's paradox after the mathematician who eventually solved it. And this was the University of Berkeley in 1968. They had the grad school, people applied for the master's things on different schools. And this was 68, the race of first wave of feminism had really come into importance. So somebody looked at all the numbers for the university to see how are the distribution of students on the different faculties. And they found clearly at the University of Berkeley in 1968, far more women were rejected at the master's level than male students. And of course, this created an outcry. It was accusing of sexism and so on. And the university said, we are really sorry, this should not happen. So what we're going to do is that we're going to look at the numbers for each individual faculty. And then we're going to figure out which faculty is guilty because we don't believe this is widespread across the entire university. So we're going to find out who is guilty. And what makes this into a paradox is that when they look at each individual faculty, it turns out that each faculty of the 4 are completely just, maybe even a slightly biased favoring women applicants. But at the same time, there's no doubt that the university as a whole, far more women are being rejected than male applicants according to the proportions. And this is, of course, is a huge paradox. It's a hard problem. But because you are smart people, I think we shall take a 3-minute you work together and solve Simpson's paradox, and we will reconvene in 5 minutes. By the way, did you understand the problem? Was it clear? So on the number of applicants, macroscopic level, no doubt that university is sexist, and on the microscopic level, university is completely fair. So please try to think about that. How could that even happen? Okay. All right, very good. Shall we try to reconvene? So I know it's a bit bad of me, to give you like 3 minutes to solve a really hard mathematical questions. But then again, what are we going to do with our lives, right? So this is good fun. Anyone who wants to have a crack at it? Anyone think they solved it without Googling? Okay, in that case, I will tell you. Or will I? Yeah, I think I will tell you. So what happened is that there's, on the microscopic level, is a really uneven distribution of applicants. So the male applicants are kind of evenly distributed along all the 4 faculties, but the female applicants have focused almost solely on one faculty. So therefore, at that faculty, lots of women are being rejected, which is fair because, according to the number of applicants, it's totally fair. But when you aggregate the number, it looks really, really unfair because a high number of female applicants get rejected. But so that's kind of the solution, that there's an uneven distribution at the microscopic level. And that's, I think, when we're working on swarming systems as researchers, what we really want to do is to find ways to connect the microscopic and the macroscopic level in the systems, making sure that if we want to have some high-level macroscopic effect, these are the rules that we need to implement on the microscopic level. So that's why these paradoxes are important. And there's a lot of them. There's something called Brass paradox. That was a guy who was working into traffic management in cities, and he found that if you have a city with huge problem with congestion and people can't find their way, one of the best ways is to figure out which road to block. So not to introduce more roads, but to actually take away a few of the roads, and that changes the dynamics and traffic flows better. Some of you are maybe familiar with prisoner's dilemma. There's all these kind of paradoxes that takes place. It's really fascinating stuff. So the upshot of this part of the talk is really that we have been able to create mathematical models for a lot of different kind of collective behavior, that being for voting, auctions, to negotiate. How do you negotiate about certain things? That's been turned into mathematical models. How to have an argument, how to argument with your partner. Maybe you could use some of this stuff. There's a guy who called Dung. He made something called Dung-style argumentation, which is this schema that you follow to reach a kind of consensus as quick, as efficiently as possible. So maybe that's something you should look up one day. Then there are, of course, cooperative game theory about binding agents can form binding contracts and coalitions and kind of be held accountable if they break the contract, and competitive or non-cooperative game theory. All this stuff is being used widely into swarm robotic research and to multi-agent systems research. And then, of course, the question is, where does all of this leads us? I call this talk Swarmfare, when the shit hits 1,000 fans, and clearly this happens that all of this stuff now is being recommended by the Norwegian research establishment, that the Norwegian defense looks into these kind of swarming multi-agent systems. So without bragging too much, it actually leads us to Six Robotics, which is the company I work for. Because the Norwegian Defense Research Institute have had research into swarming and multi-agent systems for many, many years through a system or program called the Valkyrie, which is a piece of software. And it became so good that eventually they said we need to commercialize this so that we can make it available to the Norwegian forces. And that is what Six Robotics is doing. We have been started with the sole purpose of trying to take the swarm research from the establishment and give it to the armed forces. So we are in constant dialogue with the Norwegian armed forces to get there. So what we are doing in Six Robotics is really that we take individual drones and we turn them into swarms. So in a way, this is just an upshot of all the stuff I just talked about. The CEO of Six Robotics, Christian, used to be an operator of drones in Afghanistan, flying drone Puma stuff in Kabul. And the problem is, of course, that one drone gives you a really good way to look at things and fly around buildings or hills and whatever, to do what we call an ISR mission, intelligence, surveillance, reconnaissance. But of course, if you want 2 drones or 3 drones, now you need to add more people into this. And now you have a bunch of operators that are looking at their screens instead of looking at the environment, trying to protect their turf. So this is really not scaling at all. So what the researchers did was then to create this software package called Valkyrie, where a single operator or 2 or 3 operators can operate a large number of drones in a way which is efficient for information gathering and similar kind of missions. And of course, the drones that we are building, or rather the software that we are building, is drone agnostic. So we don't care if we fly a huge fixed-wing drone or whether we fly a small quadcopter. That stuff is kind of been abstracted away from the operator. So we have a user interface which looks something like this. This is just a part of it. There's also some panels and buttons. What is set up here is a map area, the blue line, defense or geofence, making sure that if somebody tries to command a drone outside of this fence, then it automatically is going to prevent itself from flying too far away, so that we have control and control over the drones. And then you can see the status of each drones, what are they seeing. So you see this blue shade indicates where that drone can see with its sensor. And there's some terrain occlusion, there's some height above ground, there's some battery level. And all these yellow dots are different observations that have been done by these drones. What have they actually found out in that terrain? And the two yellow outer lines is just about the technology that we use to do geolocalization, because you know that in conflict areas, there is insane levels of jamming, so GPS and similar services are mostly not available. So we have other services that makes our drone knowing where they are in the terrain. And we do like this, then we can really think that the operator of the Valkyrie system doesn't tell each drone where to fly or what to look at, but he or she will communicate his or her intention to the system. What needs to be done? I need to find all vehicles. I need to find all people. I need to screen this access to make sure nobody crosses this line. All these kind of things. These are high-level abstract commands that the operator can give to the system. And then there are all these algorithms that we have talked about, negotiations, there are auctions, all these kind of things that the drones will then do once they have been given a set of assignment and intention, and they break that down and say, given that this is the intention, they negotiate, and then within milliseconds they know how to execute the mission. And that is where the autonomy and where the magic happens. And of course then that's being sent on to the flight controller that flights the drone, moves the drone to the right position, and so on. So that is kind of where the magic interaction happens between the user who has needs and the drones that do this. And because the drones do this, the operator can then say that you are flying 10 drones, you are monitoring an area. And if the operator says, hey, actually, I need 3 of you guys to go and look at something that happens over here, these 3 drones will go over there, and the remaining drones will instantly renegotiate what is now the optimal distribution and the optimal way to solve the problem, given that the numbers have changed. And this is what happens in the kind of the Valkyrie software stack, that this happens autonomously within milliseconds. So that's what happened on that level. So yeah, exactly. So as I said, the drones negotiate, participate in auctions, create a common understanding of reality so that they can execute their mission efficiently. And the whole point here is really that we need to have more drones, we need to have more machines than humans on the battlefield. And I think that we're seeing this so clearly in Ukraine. I was in Ukraine last week at Brave One. They call it Defense Technology Valley. It was a huge event with 5,000 participants in Lviv. And I talked to drone manufacturers, and there are so many companies down there now that produce maybe 50,000, maybe 100,000 drones per month and put it out in the field. And their attrition is insane. They are missing all the time. They try to strike, they miss, they create autonomy to get the last tactical mile so they can hit. And the rate of innovation is absolutely insane. If you haven't been down there, I really recommend, as engineers and as people who are, as many of you in the defense field, do take a trip. There are lots of really good people who arrange these trips all the time. I can strongly recommend Danish Innovation Highway. Espen is amazing. So do this. It will definitely change your perspective on technology and warfare forever. It's really, I get moved by talking about this because it's really, it makes a lasting impact for sure. So please do go down there and try to understand what's going on and figure out how you can contribute. It's really important. Yeah, and it reduces, turning back to this, more drones than humans, and then reduce the cognitive load of the operator so that the operator can kind of stay on the high level, abstract what's going to happen, and drones figure out how to do it. And I think that was 50 minutes, and this is my last slide. Valkyrie is built by users, for users, together with Six Robotics and the Norwegian Defence Research Establishment. So thank you very much for your attention. We have some time, so if there are questions, please come with the questions. And before questions, I will say one more thing, and this is really important, maybe the most important message of today. Six Robotics were 2 people a year ago. Today we are 40, and we are going to be 50 by Christmas and probably 70 by Easter. If any of you want to live in Oslo instead of Kongsberg, If any of you guys want to contribute this amazing mission to bring swarms to the world, please do come talk to me, and we can start a process to onboard you onto Six Robotics. Thank you very much. Now I can take questions. Yep.
So the software you showed to control the swarm, does that need like constant communication with the swarm, or will the swarm just carry out its objectives if connection is lost for some reason?
It's a good question. So because we use the communication also to do collision avoidance and all that kind of things, the drones are communicating with each other relatively often, more than once per second. But sometimes we don't want anyone to know that we are there. So there is like a ghost mode available, and then the drones will be a little bit more cautious about how close they can fly to each other. And then they can go out into an area in dark mode. They can do all the information gathering and so on. And once they come back, they can then go back online and share the information. So yes and no. So we do prefer them to communicate to make sure we have control, but they can also go and work in a kind of dark mode state. Okay, good question. Anyone? No?